Hello everyone, my name is Avinash Pawar. I am from team D13. So let me explain our project from the beginning, starting from light falling on the sensor and how our chip works. There are 285 million people in the world who cannot see properly. Are you know what? Almost 60 to 80% of their accident happens in the low light. Like when they enter in the dark room or light suddenly goes off at night. The problem is there is no simple, cheap, low power device that can give them an instant warning when they become a dark, when it becomes a dark. Current solutions are either too expensive, too big, or they need too much battery. So we brought why why not make a simple chip for this? And that is exactly we are trying to build during this chipathon. So here is our idea. We made a small patch like a band that the person wear on their waist. On the patch, there is a small light sensor called photodiode. When light becomes too dim below the safe level, our chip detects in less than 1 microsecond. That is extremely fast and it immediately gives a vibration alert or beep sound to the person. And the best part, the whole chip uses less than 50 microwatt of the power. So the lifespan of this chip is more than 1 year. So let me explain the architecture diagram. So first, light fall on the photodiode. As light changes, a voltage called V patch is generated between 0 to 2.8 volt. Secondly, inside the chip, we have a circuit that creates a fixed reference voltage of 3.06 volt. We call this is a threshold voltage. This is our safety threshold. A third one, our comparator circuits continuously check is V patch more than the threshold voltage. If V patch goes below the threshold voltage, it means it's a too dark. The output goes high and alert is triggered. So here is the complete signal path from light to the alert fires. Here is our full schematic of comparator circuit design. We have 9 transistors in total and they are organized in the three blocks. Block 1 M6 to M7. These two create the reference voltage of 3.06 volt. Block 2 M1, M2, M3, M4, M5. This is the main comparator part. M1 and M2 compare the two voltages. M3 and M4 are low transistor. M5 controls the current. Block 3, M8 and M9 are CMOS inverter. This is the output stage. It converts the comparator results to a clean digital signal, either 0 volt or 3.3 volt, to drive the buzzer or vibration motor. On the other side, we can see 6 pin uh, IC that we are planning to develop during this chipathon. So here is the Xkim implementation. Xkim is the open source software. Using this open source software, we develop our schematic. For to developing our schematic, we use Global Foundry 180 nanometer PDK. Xkim, ngSpice and Magic Layout, these are the open source tool that we are using for our schematic design and implementation. So let's see the W by L ratio. The table shows the width and length of the transistor, which we call the W by L ratio. This is the most important part of our design choice. M1 and M2, our input transistor. We we have highest W by L of 22.9. We made them so big because comparator is very sensitive to even a small voltage difference. M3 and M4 same size as each other. This matching is very important. Otherwise, output will have an error. M6 and M7, their W by L ratio difference is what set our threshold at 3.06 voltage exactly. M8 and M9, the output inverter. M8 is wider because PMOS transistors are naturally slower as compared to the NMOS transistor. So we keep PMOS wider. So here is our result. First result is a transient analysis. You can see the three lines on the graph. Blue line is the output, orange is for reference voltage 3.06 volt, and red one is the input, that is a V patch. You can clearly see at the exact moment V patch crosses 3.06 volt, the output switches instantly. The switching happens in less than 1 microsecond. The output goes from 0 to 3.3 volt. Let's see the AC analysis. This is the frequency response. Our chip works correctly up to 100 megahertz bandwidth, but we only need 1 megahertz for our 1 microsecond response. So we have 100 times more bandwidth than needed. This gives us very safety margin. Let's see the performance summary. So the power consumption is less than the 50 microwatt. Response time is less than 1 microsecond. Offset voltage is less than 5 milliwatt. Output swing is in between 0 to 3.3 volt, and threshold is stable at 3.06 volt. Thank you for uh, listening our presentation.